Hello again. When I was young, there was a fashion for sensitivity training. It basically meant you join a group of unknown others and then start digging in the mud of your childhood experiences and subconscious drives. As you may expect, this frequently led to violent emotions. Sensitivity analysis of an agent-based model is a bit similar. It means pushing and pulling all the variables to see what the model will do. Which variable settings will make the model do strange things? In the case of a model, we don't need to be gentle, as we would have to be with people. Let's take our model with the greedy and cooperative cows. Under default settings, the greedy blue cows always drive the cooperative red ones to extinction. But this switch here makes the red cows able to chase away the blues from their patch. As a result, the blues start to suffer. And if I turn the switch off again, they can recover. Now let's think. Could there be parameter settings in the original model without that switch that would allow the two breeds of cows to coexist? Let's have a look at the possibilities. To begin with, they have a stride length that determines how fast they are. It's normally 0.08, and now we halved it. And here you see what happens. I run it very fast, because it takes a long time to stabilize. You see, actually, the blue cows suffer. They eat away everything under their feet. They are still able to displace the reds, though, and that compensates. So in the long run, you get this equilibrium that doesn't quite stay in one place, a dynamic equilibrium, about 3/4 reds and 1/4 blues. So, for our sensitivity analysis, we can conclude that the model is sensitive to the parameter stride length. If we reduce it any further, what do you think would happen? It's a no-brainer, right? So the moral is greed loves speed. Now, let's go back to default parameters, so stride length back at 0.08, and have a look at grass energy. It's normally 51, and we're putting it to 20. So the nutritional value of the grass is lower, and as you can see, the blue cows die out very quickly because they eat everything on their patch and they cannot get away, and they're still hungry, and so they are then too slow to get away. Now we try 27, stride length 27. Let's run it. And you see a bit of the same, but here the blues still survive, and you can see in the graphs, again, you get a sort of dynamic equilibrium with quite a lot of variation, and that variation seems to have something to do with the spatial pattern. The blues leave empty spaces that are sometimes not found by other cows, and sometimes they are, and so that makes these numbers fluctuate. For our sensitivity analysis, we can conclude the model is also sensitive to the parameter grass energy. The last parameters we'll test for sensitivity are the high growth chance and low growth chance of the grass. If the soil is here, this is the low grass, this is the high grass. The red cows only eat this. The blue cows also eat this. And where they coexist, they will eat only this. So, if we go back to default settings and then we reduce low growth chance, as we did here, we are biasing the food supply away from the blue cows because they are the only ones eating that low grass. Again, you see coexistence happens. The blues are almost but not quite exterminated in the long run. So, grass energy and low growth chance seem to have similar effects in the model. Now let's look at behavior space. It's the built-in facility that NetLogo has in its tool menu for carrying out sensitivity analysis. We can define the values of various parameters that we want to run the model with, the number of repetitions per setting, the variables we want to show, and the number of ticks we want to run it for, and then let's go. In this case, we have to run for at least 5,000 ticks because it takes 1,000 ticks or so for the system to stabilize, and after that it starts to have its oscillating behavior. So we have here an analysis of combinations of 3 variables at 2 values each, and 10 model runs per setting. That's 2 times 2 times 2 times 10, 80 runs in all. And when you run this experiment, you click run here, the model will run 80 times, and then generate a file that you can process with R or Excel or SPSS or whatever you like. In a serious sensitivity analysis, we'd have to check for each parameter of the model. We haven't done that here. And also for combinations of settings of different variables. And if there is randomness, we might see differences between sessions with the same parameters. So we should do many runs. We did that here. We did 10 runs. The more runs you do, the lower your standard deviation that you have. So, concluding, you have seen how sensitivity analysis can reveal which parameters matter the most for model output. If a model is not sensitive to a certain parameter, well, it shouldn't be in the model, right? You can already draw a moral for model building, which is keep it simple, or you will be making your life hell during sensitivity analysis.